Moment here. I forgot to record this. I just turned it on. Now I got to take another picture of it.
Okay.
All right. Okay. So FOIL it.
Okay. So it'll be x cubed and then 4x plus 4x minus 3x squared minus 12.
Now notice you can't combine any of that.
Mm-hmm.
So might as well just start differentiating. In other words, we don't have to do any simplification. And it doesn't matter that these are out of order. In other words, typically you write a polynomial with the highest degree and then the next highest degree and so forth. And we could do that, but you don't really have to. Just use the power rule on each term of that polynomial.
Okay.
What do you get?
3x squared plus 4 minus 6x.
Okay. What's the other way to do this problem?
I can't remember the names right now.
Product rule.
Yeah, the product rule.
Product because they're being multiplied. Okay? So let's use the product rule this time. Make sure we come up with the same answer.
Okay.
This is U, that's V. Or if in your class they call that G of X and that's H of X. Basically I have two different functions that are both functions of X. So the product rule says what?
I completely forgot how to do this one.
Okay, it's the first term times the derivative of the second term. And this is a plus, meaning you can actually do it in the other order if you want, but the rest of it's the reverse. What's the reverse of that?
The first term, the derivative of the first term times the second term.
Yeah, now see here you don't really want to memorize the whole thing. What you want to do is memorize that plus the reverse.
Okay.
It's easier. Again, operating on the principle of never memorize more than you have to. So, in this case, get me started. I always like doing U first, always. I never do U prime times V plus U times V prime. Mainly for one reason, the biggest reason is I can never tell what the student's doing. So when I ask you to differentiate it, if you do it in the order that I am not accustomed to, I'm not sure that's what you're doing. So I finally decided to solve that problem by telling all the students to always do it in the same order that you learn it. Pick one order and stick with it is what I'm trying to say.
Okay.
And the order that I like is where you start with U and then do V prime and then add the reverse. So let's
Okay. So if we want to leave U, x minus 3,
okay.
and then 2x plus 1
Yep.
times 2x.
No, you don't take the derivatives of both. Remember, each of these terms, that term, you didn't take the derivative of U. This term, you don't take the derivative of V. You leave it. This is all, in other words, you took the derivative of U here. What this is U times V prime plus U prime times V. You're never taking the derivative of both, whether it's the quotient rule or the product rule.
Okay.
Okay, you have one term times the derivative of the other or vice versa, but you never have two terms where you're not differentiating one of the terms or where you're differentiating both terms. That doesn't happen on any of these rules. So let's simplify that now. This is actually the easier way to do it, I think. You will agree. In other words, doing it the other way, you had to FOIL it first. Now, granted, once you FOILed it, it became pretty easy. But this becomes pretty easy too. We'll simplify this.
2x squared minus 6x plus x squared plus 4, and then 3x squared minus 6x plus 4.
One advantage is you ended up with a polynomial that had everything in the right order.
Mm-hmm.
Whereas the other way, same answer, but I think the other way actually is a little more work. And you want to use the product rule where you can, I think.
Okay.
Not always the quotient rule. Notice that a lot of things like that looks like you'd have to use the quotient rule, right? But what if I made that, say, x plus 5 times x minus 1 to the negative 1? Now I could use the product rule. And believe it or not, that's very easily done. On 36, I can write that, e to the x times x to the minus 1. Now I can use the product rule. And the product rule, the reason I used to always do that is because I couldn't be certain I had the quotient rule memorized right, because nobody had taught me that little ditty. So I generally changed quotients to products and went from there, because I knew what the product rule was. Well, you can do it. I'm not suggesting you'll ever do that, but know that you could. In the same way that that can be written, or that can be done using just the straight power rule or the quotient rule. Obviously, the power rule is easier, right, than the quotient rule. I mean, the quotient rule is a pain in the butt.
Yeah, definitely the power rule is way easier.
Yeah, for sure. So really, you want to use whatever technique is the easiest to use. All right, what's the next question we want to do?
And then the next is 8 through 12.
8 through 12 inclusive?
Yep.
Okay.
Yeah, all of it.
Start with 8.
So would it just be 6 minus 2x e to the x?
What do we have here? What do we have to use there?
Limit? No, natural log.
Power rule. Not the natural log. The the product rule. I meant to say product rule. Why? Because we have two functions multiplied together. We have 2x times e to the x. And there's no way to simplify that. I cannot combine those two terms. The only way I can differentiate it is by using the power rule. Okay? And you got to be a little careful here in that you want to make sure, and parentheses are extremely important in calculus. If you don't get in a method of using parentheses, you're going to miss a lot of signs on stuff. Because I'm subtracting that whole thing, the derivative of that whole thing. And the derivative of that whole thing is going to be, we know the product rule, you end up with a plus b, right? So I need parentheses around the answer. So let's differentiate. There's the negative sign, so I don't have to account for the negative sign. But what is the derivative of 2x e to the x? Let's just work with that. Let's assume that's y. What would y prime be?
Would it be 2x and then times e to the x? Then just 2 times e to the x.
So all of this goes in these parentheses. In other words, that is what's in the parentheses is the derivative of 2x e to the x. And now you can kind of see why the parentheses are so important. Because when I remove them, I get 6 minus 2x e to the x minus 2e to the x. If I didn't have those parentheses in there, that plus sign is going to mess me up.
Okay.
Most important time you need parentheses is when it's after a subtraction sign, where the entire quantity is being subtracted. I'm not just subtracting 2x. I'm subtracting the derivative of that, which is everything I have in the parentheses. And then when you remove the parentheses, which they're always going to have you do in order to simplify it, you end up with what I have written at the bottom. Okay, number 9. Well, I don't have a lot of blank space to write here. Hold on a second. Let me see if I can move this thing up. Yeah, I can a little bit. That'll help a little bit. Yeah. Okay. What rule are we going to use on number 9?
Product rule again.
Okay. So what's f of t? Or what's f prime of t?
It would be t to the 5th power times, would it be the natural log of...
No. Doesn't matter whether it's e to the x or e to the t or e to the r. If it's a function of t, then it's e to the t. That's the derivative of e to the t.
Oh, yeah.
Okay. Now, plus what?
Plus 5t to the 4th power times e to the t.
There's your answer.
And then
you could factor some of that, but I don't know that it's necessary. In other words, I could factor out an e to the t. So I had this as a final answer. If it was a multiple choice test or something, you might see this as the final answer. Make sure you understand what I did there. Just factor out an e to the t.
Okay.
Not that you have to do it. Mainly the reason you factor is if it allows you to simplify further. In other words, if this whole thing was being divided by an e to the t, it would have been really worthwhile to factor out that e to the t, because now I can do that and I'm left with a much simpler answer. But the factored answer isn't that much better than the raw answer that we got when we just did the initial problem. In other words, there really wasn't any simplification required on 9. Okay, let's do 10. What's g prime of w equals? What rule?
I mean, product rule again, I guess?
Always. Product rule is huge. You're going to have to use it a lot. There's no other way to do it. I can't really, I wouldn't really want to multiply this out, right? Because then I would have that, I'd have to use the product rule, and then I would have that times e to the w. I'd have to use the product rule again. So it's better to just treat these as two entities and start right off.
Okay. So, I would start with e to the w times 10w plus 3 plus e to the w times 5w squared plus 3w plus 1. And yeah.
This one, there might be a reason to multiply it out. You'll notice that I'm going to end up with a 10w e to the w over here when I multiply those two. And I'm going to end up with some number of e to the w times 3w. So if I distribute these out, I'll be able to do some simplification. In fact, let's do it. Let's make sure you understand what I'm saying here. In other words, that's not my final answer because I can do quite a bit of simplification here. First of all, I'm going to distribute. You with me?
Yeah.
And now I'm going to have some like terms that I can combine. Well, how many of those do I have?
None.
13. I have, excuse me. Notice what I can do here. I didn't notice this when I first looked at it, but now I see it. You think this is going to help. Every one of these terms has an e to the w in it, right? Factor that e to the w out, leaving us with 10w plus 3 plus 5w squared plus 3w plus 1, right?
Yeah.
Now I can combine the 10w and the 3w. That's 13w. That's my simplification. I can also combine the 3 and the 1, making it 4.
Cool.
And that's it. So my final answer would be significantly simpler. I'll put the 5w squared first, and then 13w plus 4. So there would be my final answer. And I think if you were looking at multiple choice answers, this is what you'd find. But notice that that is quite a bit simpler than that. In other words, you want to do factoring whenever you can combine anything, and when you can combine like terms, you want to do it. If you have to factor first to do it like I did here, then that's what you want to do.
Okay.
$11. What are we going to do here?
I guess power rule again.
Yeah, again, you have a choice. You can multiply this binomial times this quaternomial, quartic, rather. And then you're going to have a 5-term polynomial that you could just apply the power rule to quickly. So, but again, let's practice the product rule here. So what's h prime equal to?
It'll be x minus 1 3x squared plus 2x plus 1 plus 1 times x cubed plus x squared plus x plus 1.
Again, I'm going to have, I can see right away that that times that produces an x squared, and I have an x squared over here. So by distributing these and removing parentheses, I am going to be able to combine some stuff.
Okay.
Okay, let's not take the time to do that just because we're trying to learn calculus, not algebra. I trust you know how to do that.
Okay.
In other words, you know how to remove these parentheses and then combine like terms. But as we can see, this is going to be a little harder because we do have to multiply this binomial times this cubic before we can combine like terms. So it might have been easier all along to just multiply them out in the first place, and then we'd have had a 5-term polynomial that we could have used just the power rule on. So some problems, maybe one method is a little easier than another. I don't know. I would say always use the product rule. It's usually not going to be a good idea to multiply them out. Let's do number 12 using the product rule. So first of all, tell me how to write it in its original format. If I'm planning on using the product rule, how would I write it?
So it'd be 1 plus 1. No, yeah, 1 plus x squared. X negative 2.
There you go. In other words, in order to use the power rule, you have to have x in the numerator. You can't use the power rule when x is in the denominator. Okay, so there's our two products. Now, tell me what f prime is.
Wait, what do you mean?
Now we're going to use the product rule. This is u, this is v.
Oh, okay, yeah. So then it would be 1 plus x to the negative 2 power times 2x plus negative 2x to the negative 3 power plus, wait, no, times x squared plus 1.
Good. And again, there's further algebra to be done. Almost always you're going to be able to, in other words, when I do multiply that by that, I'm going to have an x to the minus 1. When I multiply that by that, I'm going to have an x to the minus 1. So I'm going to be able to combine those like terms. So I'm not done. This is not the final answer. Whenever you can simplify, you're supposed to do it. Okay? It's just I don't want to spend the time doing that algebra. I'd rather talk about calculus. If you have any questions, don't let me end that problem early if you're not sure how to go from here. Okay?
Okay.
What's next after 12?
12, 24 through 28.
Okay. Yeah, this is good stuff. If you hadn't have given me this, I was going to give you a page of almost exactly the same stuff. Just lots of practice on doing the product rule, power rule, quotient rule, and chain rule. Actually, this is not giving you much practice on anything but the product rule, although these are going to be quotients, okay? So we're going to have to use the quotient rule on all of these, or they're asking us to do. Derivatives of, well, they actually aren't asking us to do that, are they? In other words, we wouldn't actually have to use the quotient rule on that problem. We could use the product rule. Those two things are being multiplied together. But derivatives of quotients, let's go ahead and get some practice in on the quotient rule here. I think it wants us to do these using the quotient rule. How should I rewrite that, first of all?
I would write it as e to the negative x.
No.
Times.
We're going to use the quotient rule. I'm going to need a denominator.
Oh, okay. So it'd be x to the 1/2 over e to the x.
Good. Now use the quotient rule.
Okay, so it would be x to the 1/2.
Always follow the same pattern, Jake. What do you start with? What do you end with?
The bottom and end with the bottom.
Okay, so I'm starting with the bottom. I'm not starting with anything that has to do with the top. I'm starting with the bottom. Since I'm taking the bottom, what has to be multiplied by it would be the derivative of the top. So now what's the derivative of the top?
1/2 x to the negative 1/2.
Okay. Since order matters, it was really important that we started with the bottom, not the derivative of the bottom. Well, the only way order could matter is if subtraction is taking place. What's the rest of it?
Then it would be minus e to the x again.
Which is the derivative of the bottom.
Yeah, and then x to the 1/2.
Good. And all divided by, end with?
The bottom squared, so it would be
e to the x squared.
e to the 2x.
Yep. Now, again, and let's do it here, because I see that it's very practical. What would I want to factor out? Would I want to factor out the x to the minus 1/2, which incidentally you can do. You're probably not used to doing that, but when calculus, you end up learning how to do that. In other words, I could actually factor out an x to the minus 1/2 from the numerator. Both x to the minus 1/2 and x to the 1/2 are both divisible by x to the minus 1/2. So I could accomplish something, but it wouldn't be much. Whereas if I factor out the e to the x, now I can accomplish a lot. Factor out the e to the x and tell me what we have.
Then you have 1/2 x to the negative 1/2 minus x to the 1/2.
Now notice what we can do. Because I'm dividing the whole thing by e to the x times e to the x, that's what e to the 2x is. Now I can cancel that with that. And what I'm left with is a simpler answer. Now, I could still factor out an x to the minus 1/2, but it doesn't do anything. It doesn't do any good to do that. Whereas it did do some good to factor out the e to the x, because I had one in the bottom. And that's how you kind of have to proceed with some of these, especially when you're using the quotient rule. The quotient rule is easy to apply if you just remember start with the bottom and end with the bottom squared. What's difficult is simplifying it after you've done that. It's almost always more complicated. In other words, there's usually some manner you can simplify it. Okay, how about 25? Rewrite 25. So that we get the quotient rule.
So it'd be 3t minus 1 over 2t minus 2.
Now apply the quotient rule.
So you'd start with 2t minus 2.
In parentheses.
Yeah, times.
You're never sure to add parentheses. It's never wrong to add them. You can even if they're not necessary, you're not going to make a mistake by adding them. But it's easy to make a mistake by not putting them in when you need them. Times what?
Times 3.
Okay, now you see why I need those parentheses? It's a different problem altogether if I leave them off. Different answer.
Mm-hmm.
Minus
1. And then minus 2 times 3t minus 1.
All over. All over
2t minus 2 squared.
Yeah, now I would not normally expand that. Nothing to be gained by it. And it's possible, let's see, this becomes 6t plus 2. I cannot get a 2t minus 2 out of that. Now maybe, hold on a second, let me up here in the right, I'm going to distribute the numerator. Let's just see what we have. We might be able to simplify this a lot. Okay, I've got that on the left, and then I'm subtracting 6t plus 1. Here I don't want the parentheses. In other words, I'm definitely subtracting that, so I'm going to have a minus 6t, but then the minus 2 times the minus 1 is plus 1. Okay?
Okay.
Notice what happens. The 6t's cancel, and I end up with minus 5 in the numerator. My denominator is still 2t minus 2 squared, and that's my best answer. That's my simplest, most simplified answer. But once again, you can see that you're never done when you just fill it in to start with. In other words, when you've done this part, there's almost always more work to be done. And the way to proceed is just simplify the numerator and see what you got. I didn't see it when we first looked at it that the 6t's were going to cancel, but they do. But maybe they wouldn't. Maybe this would be 5t, and so I'd be left with a t in the top, but it would still be simplifiable.
Okay.
And always look for that with the quotient rule. It almost always is simplifiable. Okay, 26. It's already written in good form.
Yeah, so it would be w squared plus 1 and then w squared minus 1. No, 2w minus 2w again times w squared minus 1. All over w squared plus 1 squared.
Okay, simplify the top.
The top, so it would be 2w cubed plus 2w minus 2w cubed, yes, squared.
No, cubed is right. W times w squared is w cubed.
Minus 2w.
Plus 2w.
Plus 2w. Oh, yeah, you're right.
That times that.
Okay.
So it's plus 2w. And all over w squared plus 1 squared. But let's simplify that. I see there's some simplification. What's that simplified to?
Just 4w.
And the bottom doesn't change. There's no point in expanding it. Won't advance the problem or allow us to simplify. That's as good as I'm doing. $27. At least they've made them a little bit easier in writing. As opposed to 25 and 28.
Yeah, that's kind of absurd.
Well, it is a little bit, but it does teach you something. Teaches you nothing else. It gives you practice at negative exponents. Like this one wasn't that clear how to write. That's x over e to the x.
Yeah.
Okay. All right, 27.
So it would be x squared minus 1 times e to the x minus 2x times e to the x all over squared minus 1 times 2.
Not times 2, but squared.
Oh, yeah, sorry.
Okay. Now, if I look at this quickly, I can see that I could factor out an e to the x from the top, but it doesn't do any good. There's nothing in the bottom that I'll be able to cancel it with.
Mm-hmm.
And I can't really factor out anything else. It'd be nice if I could factor out an x squared minus 1, because then I'd have some of those in the bottom that I could cancel it with. But I can't. So I'm done. That's my answer. There's no point in, I don't think there's any point in simplifying it. No. If I distribute it, I get e to the x squared minus e to the x minus 2x e to the x. There's no simplification. There's no like terms there. So
Okay.
I can't combine any of that. I got to have a like term. Look, some number of those. Well, I got a 2x e to the x, but that's not 2x, that's x squared. So I could factor out an x, but that doesn't really do me any good either. So my general rule is you don't factor just because you can. You factor only if it allows you to simplify further. And that's really not going to allow me to simplify further. Okay, 28. Let's write it properly for calculus.
Mm-hmm. What?
Rewrite 28 to prepare us to use the quotient rule.
So it'd be 2x to the 1/2 power minus 1 all over 4x plus 1.
Now apply the quotient rule.
So I would go with
Always start with the bottom. That is so simple. Just always start with the bottom.
okay, 4x plus 1 times 1. No, just times x to the negative 1/2 power minus x.
Not x. Now we're taking the derivative of the bottom. In other words, the reason you start with the bottom is you're not starting with the derivative of the bottom. You're always starting with the bottom, which means after the subtraction sign, you got to take the derivative of the bottom next.
So,
times the top.
oh, okay.
In other words, just the reverse of the first part. This is the bottom times the derivative of the top. This is the derivative of the bottom times the top. All
Okay.
over 4x plus 1 to the what?
To the 2nd power.
Yeah, you start with the bottom, you end with the bottom squared. Now, can we simplify that? Gosh. The only way I would be able to simplify it is if I can pull out a 4x plus 1. Let's see. I actually end up with 8x to the 1/2. Yeah, and I got an x to the negative 1/2, but it's not to the positive 1/2. Although when I multiply this by this term, in other words, when I multiply these two terms, I do actually get something that I can simplify. And we better make sure we show you. That's the hard part of these, so we don't want to omit that. Okay? So when I multiply the first two terms, what's 4x times x to the minus 1/2?
I don't know.
The base is the same. You add the exponents. Well, there's a 1 right there. 1
Oh,
minus
so
1/2.
so it'd be 4x 1 and 1/2.
No. You add the exponents. That's a negative 1/2. That's a positive 1. So when I add those two, I get 1/2. So when I multiply that by that, I get what I've written up here. Plus 1 times that, so plus an x to the minus 1/2. And then let's distribute the other part.
8x minus 4.
Give me a sign. Always need a sign.
Negative 8, minus 8x to the 1/2 plus 1, plus 4.
Now, can I combine any of that?
You can combine the x to the half powers.
Yeah, what do those combine to?
12x to the 1/2.
Nope, I got 4 minus 8.
Oh, no, so it'd be negative 4. Sorry, I forgot the signs.
Okay, that takes care of that term and that term. I don't see anything else I can combine, so I'll just go ahead and add the rest of it. In other words, I can't ignore it, but I can't do anything with it. And my denominator is still 4x plus 1 squared. And I don't see how I can take any of that out of the numerator, so that's my answer.
Cool.
I think. Yeah, has to be. Yeah. Let's see how much time we got. I want to take you through this process just to show you. You might not be familiar with doing this. I want to make sure you understand what I'm talking about when I say you can factor out an x to the minus 1/2. In other words, when you find yourself with a bunch of fractional exponents, some are positive, some are negative,
Yeah.
factor out the negative one. Factor out x to the minus 1/2. What's left over? Remember what you're doing when you're factoring is you're dividing each term by your factor. So when I divide minus 4x to the 1/2 by x to the minus 1/2, what do I get?
You get minus 4x to the negative 1/4.
No. Remember, I'm dividing. I'm dividing x to the 1/2 by x to the minus 1/2. Subtract the exponents.
Oh, so it's 4x.
Yeah. And then I'm going to factor out an x to the minus 1/2 there. So that's plus 1. Now, there was, I don't know. I don't know if I erased something here accidentally or not. I don't care. I really didn't want that there anyway. Okay, as all I'm doing is dealing with that. And you can factor out an x to the minus 1/2. And sometimes that's going to be very useful because I may have an x to some power in the denominator, and then I can simplify it further still. It's just not something you're used to doing. Have you ever factored out something that had a fractional exponent? Well, you can do it and use the negative exponent. You could also factor out an x to the 1/2, but x to the minus 1/2 works out nicer. It gives you nice positive exponents because you're looking at doing that, which turns into x.
Okay.
Okay? So, and you will need to be able to do that on some of these where it allows you to simplify it further. All right, so we've done through 28. What else we got? We got about 5 minutes. What else can we do here?
And then 31.
Did you say 41?
No, 31.
31. Okay. Is that up top on the right? Probably. Okay. What's the directions on this? Same as they are for the bottom. Derivatives by two methods. Use the quotient rule to find the derivative of the given function. Find the derivative by first simplifying. Okay. So I'm a big believer in using the easiest method, which is not the quotient rule. Since we only have 5 minutes, let's use the easier method, and if we still have time left over, we'll use the quotient rule. But we don't really need the quotient rule on this. Simplify that. 31. What's the top look like?
2x minus 2a.
No. You can't start applying the power rule. We got a quotient here. If you're gonna use the quotient rule, you got to start with the bottom.
Okay, so it would be
Is the quotient rule. Factor the top. What is that called? That's difference of perfect squares. How's it factor?
I don't know actually.
A squared minus b squared factors into what? Gotta know this. This is huge.
I don't actually.
Okay, it factors into x minus a times x plus a. You did know it, you just forgot it.
Okay.
Right? In other words, x squared minus 4 factors into what?
X plus 2x minus 2.
Okay.
So I'm just thinking it in variable form.
You didn't know. Yeah, the only thing that confused you is the letter A. But that's a constant, so that's just a number. Okay? Even if it was a variable, you'd still factor it this way. Okay? And now that's over x minus a, and now what can I do?
Cancel.
Now take the derivative of what's left.
1 plus 1.
Not 1 plus 1, 1 plus 0. The derivative of a constant is 0.
Oh, yeah.
So that's the answer. Boy, it doesn't get any simpler than that. Now, if we were to apply the quotient rule, and it says do it 2 different methods, so give me that.
The quotient rule?
Uh-huh.
So, x minus a times 2x minus 2a.
Just 2x. Remember, a is a constant.
Oh, yeah, sorry, I keep forgetting that.
A is a constant, a squared is a constant.
Okay. Minus 1 times x squared. Yeah.
All over x minus a squared. Now, that whole thing's going to turn into 1. So you tell me what's the easier way to do this. The first way we did it or this way. But just to prove it to you, I'll distribute it. 2x squared minus 2xa minus x squared plus a squared. All over x minus a quantity squared. All right, let's see. 2x squared minus x squared is an x squared minus 2xa plus a squared all over x minus a quantity squared. Well, how's that factor? That factors into x minus a squared.
Yeah.
See why? Which is x minus a squared divided by x minus a squared. We get 1 again. So,
obvious which way is faster.
Yeah, by a lot. In fact, the second way, you might be hard-pressed to come up with 1. That, like I said, the algebra is what's tough on all of these, quotient rules particularly. Combining and simplifying is the really difficult part. That's where you really need good algebra skills. All right, Jake, It's a good place to stop. We got a lot covered tonight also.
Yeah, yeah.
The last two sessions have been really good, I think.
Yeah. Yeah, I agree.
This is the crux of differential calculus. Now, by the crux, I mean this is what you generally have to do most of the time in terms of legwork. You haven't really gotten to real problems yet where you've used calculus to solve something, but you will. It's called optimization problems. And those, trust me, this is all headed somewhere. At this point, it's just pure math. But the reality is this is going to let you solve problems that couldn't be solved in any other way other than using differentiation. We'll get to those. You're not quite there. You're probably a week away from that.
Okay.
Next up, they're going to let you practice the chain rule. I noticed that we didn't have any chain rules at all in this. So
yeah, I guess
there's still some practice on the chain rule you need. And then implicit differentiation, which we talked a little bit about last time. You'll get another session on that. So we'll still probably have a couple sessions on those two subjects, and we need them. Those are big subjects. I felt the only thing I didn't like about our last session was that we covered like 6 big subjects in 1 hour. That's too much. You need like an hour for each one. The product rule, another hour for the quotient rule, another hour. Chain rule will be harder. Chain rule is the hardest one of all. But not if you look at it right. The trick with the chain rule is to figure out what the inside is, very first thing. And then take the derivative of the outside, multiply it by the derivative of the inside. But figuring out the inside is the tough part.
Yeah.
Jake, have a nice night, and we'll talk to you tomorrow, I think.
Yeah, well, thank you.
You're welcome. Bye-bye.